In this video, we're going to look at a number of properties of matrices. So let's recall how we add two matrices. Say A and B are m by n matrices. So they are matrices with m rows and n columns. Let's see be the sum of these two matrices. So what is C? Well, the ij entry of C is given by the ij entry of A plus the ij entry of B. So this means that addition is carried out component-wise. And here's an example. Suppose that these are my matrices 1, 2, 3, 4, 5, 6, and 1, 0, minus 1, 2, minus 2, 0. And if I add them, you add them component-wise. So this component here will be 1 plus 1, that's 2. And the next one will be 2 plus 0, so 2. And here will be 3 minus 1, which is again 2. And in the bottom row, I have 4 plus 2, that's 6. 5 minus 2, that's 3. And 6 plus 0, that's 6. Now, there are a number of properties that are worth remembering. So suppose that A is m by m, B, C, and D are m by n. Then the following properties hold. The first one is known as associativity of addition. So adding C and D first and then add to B is the same as adding B and C first and then add D. And the second one is known as the commutativity of addition. So B plus C is same as C plus B. And the next one is known as the distributive law. A times B plus C go A times B plus A times C. And there's another one similar. And B plus C times E is the same as B times E plus C times E, where here E is n by n. Now, the next set of properties that we're looking at concerns what is called a scalar multiplication of a matrix. So let alpha be a scalar. And if we're working over the real numbers, alpha will be a real number. And let A be a matrix. Then when we write alpha A, it is the matrix obtained from A by multiplying each entry by alpha. So for example, suppose we are working over the complex numbers. My scalar is 1 plus I and the matrix we are looking at is 1, 0, I, 2. Then this represents the following matrix. 1 plus I, so I'm multiplying every entry by 1 plus I, 0. And here I have 1 plus I times I, so that's I plus I squared. And so I have minus 1 plus I. And here I have 2 plus 2I. And the way matrix subtraction is defined is simply this. We take A plus minus 1 times B. And the negation of a matrix A is defined to be minus 1 times the matrix A. There are a number of properties that involve scalars and matrices. Let alpha and beta be scalars, and A and B be m by n matrices, and C be a p by m matrix. Then the following properties hold. So alpha times A plus B is the same as alpha times A plus alpha times B. Alpha plus beta times A is the same as alpha times A plus beta times A. Alpha times beta times A is the same as alpha times beta times A. And C times alpha times A is the same as alpha times C times A. And that's the same as alpha times C times A. So those properties allow us to do a lot of simplification in matrix computations. And the next thing is the notion of a transpose of a matrix. The transpose of an m by n matrix A, and is denoted by A superscript T. Sometimes the lowercase t is used instead of the uppercase t. And that is the n by m matrix such that the ji entry is given by aij, where I is from 1 up to m and j is from 1 up to n. Another way to say this is column I of A transpose comes from row I of A. So let's look at an example. Suppose that A is 1, 2, 3, 4, 5, 6. So every row becomes a column in the transpose. So the first column comes from the first row, and I will write down 1, 2, 3 as the first column. And for the second column, it will come from the second row, and it will be 4, 5, and 6. And there's another example. Say my matrix is just a matrix of a single column. Then what is A transpose? Well, again, every column comes from every row. Now the first row has only one element, so the first column has only one element. And the second column will have one element, that's 8. And the third column will have the element 9. So that's my A transpose. Now, there are a number of properties that the transpose satisfy. The first one is if you take the transpose of the transpose, you get back the original matrix. And if you take the transpose of a sum, it's the same as the sum of the transpose of each of the matrices. If you take the transpose of A inverse, then A transpose is also invertible, and the inverse is given by this. Finally, if you take the transpose of a product AB, it's the same as B transpose times A transpose. For example, if A is 1, 0 and B is 2, 3, 1, 2, well, then this transpose is, according to this formula, given by 2, 3, 1, 2 times 1, 0, which is 2, 3. But we can first compute what this is and take the transpose. So computing this will give me 2 and 3. And then taking the transpose of this will give me 2, 3.